Okay, as we move on through our sample problems in Chapter 6 here, I just want to give you a little context based on the last two problems that we did. So problem 6.3 dealt with figuring out the amount of heat that it would take to raise the temperature of the copper-clad bottom of a skillet, essentially 275 degrees. So we used this equation as is to figure out what that heat was. Our next problem here said, you know what? Let's consider heat exchange. Heat exchange between a hot metal that's put into a cool glass of water. We're going to again cool off the metal, heat up the water, and that heat is essentially exchanged between these two proportional to the specific heat capacity of the solid, which is what we were going to solve for. Okay, so what becomes new in our next problem is we're basically doing the same type of a calculation, thinking about heat exchange, but this time we're thinking about a chemical reaction that's generating heat and transferring it to our solution. So again, pictures to me always help kind of contextualize things. So looking at the problem here, we've got 50 milliliters of a 0.5 molar sodium hydroxide solution. So I'm going to take, I've got 50 milliliters of a 0.5 molar sodium hydroxide solution. They tell me that the temperature of this solution is 25 degrees C. I've got another solution here, 25 milliliters of a 0.5 molar HCl solution, also at the same temperature, 25 degrees C. I'm going to mix these two solutions together, and I'm going to do it in a coffee cup calorimeter. Anytime they tell you in a coffee cup calorimeter, that just means that we're not going to let heat escape. So any heat that is part of our system here is going to be captured and retained in our system. So again, mix these together and we're going to end up having 75 milliliters of solution. And the final temperature of the solution is 27.1 degrees C. So what happened such that we generated some heat? Well, the chemistry is that we've got hydrochloric acid plus sodium hydroxide. We do a neutralization reaction. And as we learned about in previous chapters, mixing acids and bases is a neutralization reaction, and we're just applying in this chapter that it is an exothermic process. We generate heat. Okay, so again, heat meaning that we increase the temperature. That's an exothermic reaction. So we're going to treat this exactly the same way that we kind of treated this problem here, where our system was our water that's going to be heated up. In our previous problem, we had a physical change, a cooling down of our solid that generated the heat for this process. Now we're going to have a chemical reaction. So we have a minus Q of our reaction. We have an exothermic reaction that's giving off heat, and it's going to heat up our solution. So again, our reaction is going to heat given off. That's because it's exothermic. So exothermic reactions give off heat. They're going to give that heat to our solution. And again, Q of solution here is going to be equal to the heat capacity of the solution times the mass of the solution times the delta T of the solution. So this problem asks us, okay, the first part says we want to calculate the heat that's kind of given off from this process. Okay, we want to calculate Q solution in joules. Okay, so we want to calculate Q solution in joules. And that's going to be, oh, here's A, calculate Q solution in joules. So Q solution is going to be equal to, again, heat capacity of the solution times the mass of the solution times the delta T of the solution. So information, again, that we need, they tell us to assume that the solution, right, they tell us to assume that the solution has a specific capacity of water. So we're going to assume that it's 4.184 joules per gram Kelvin. Mass of the solution, we're going to assume that the total volume of the solution is the sum of individual volumes and that the final solution has the same density as water. So we can figure out the mass of the solution by taking the volume and translating that into mass, so 75 grams. and then delta T of solution. That's going to be T final minus T initial. So that's 2.21 degrees C, and again, that's 2.21 Kelvin. Go back and see one of our earlier sample problems. If you are a little bit unclear as to why sample problem 6.3, if you're confused as to why I can directly say 2.21 degrees C is 2.21 Kelvin. Okay, so we have all of our pieces of information. Now it's just a matter of putting them in. Okay, so putting those pieces of information in, we've got 4.184 joules per gram Kelvin, 75.0 grams of solution. 2.21 Kelvin is how much that solution was heated, and so Q of solution is equal to positive 693 joules. Okay, so again, that is the amount of heat given to the solution. So that heat was given off by a reaction. It was given to the solution when the solution gained heat that should have meant it increased in temperature. And that's exactly what happened. Okay, so that part of the problem isn't necessarily all that different from stuff we've done before. We're just looking at a chemical process that generates the heat rather than, for example, a hot metal like we saw in our last problem. Now, this next part says calculate the delta H of the reaction in kilojoules per mole. So we need to quantify this. We know that this much heat is given off, but we need to quantify it in terms of the amount of water formed. Hopefully we can see if this makes sense. We want kilojoules per mole. If we know how many moles of water was made, we can qualify this. We can just divide by the number of waters. So it's pretty straightforward that delta H of reaction is going to be equal to 693 joules. Okay, and again, this is going to be reaction, so it's heat given off divided by the moles of water. All right, so we just need to figure out how many moles of water we make. Oh boy, we have amounts of 2 reactants. So all of a sudden this becomes a limiting reactant problem. Oh boy. All right, so in order to figure this out, this becomes a limiting reactant problem. All right, so again, just to make sure that everybody understands kind of where we're going from here, this is the amount of heat that's given off by this chemical reaction. What we'd like to do is qualify that and say it's this number of joules per mole of water formed. Well, in order to qualify it, we need to find out how many moles of water are formed. The only way to figure out how many moles of water that are formed is we need to do a limiting reactant problem. All right, so limiting reactant problems, we always start out with a chemical equation. So we've got aqueous HCl that we've mixed with aqueous sodium hydroxide. We make water, and we make sodium chloride. Okay, we have 25.0 milliliters of HCl at 0.500 molar. And we've got 50 milliliters of HCl, or of sodium hydroxide, excuse me, at 0.500 molar. Maybe you can look at this and you can immediately see who the limiting reactant is. If you can't, I'm going to show you mathematically how we figure it out, and then we'll come back here and hopefully you'll see it then. To figure out a limiting reactant, you have to take each species and convert it to the same product. We tended to use the method for limiting reactant determination of taking each species, going on to make the same product, and see who makes less. All right, so quick conversion into liters, 0.025 liters. Get myself a little bit more room here. 0.025 liters of HCl times 1 liter of HCl, 0.500 moles of HCl, and that's 0.0125 moles of HCl. For every 1 mole of HCl, we make 1 mole of water. So that means we have 0.0125 moles of water that we could make from the HCl provided. Same calculation for sodium hydroxide. 0.050 liters of sodium hydroxide. 1 liter of sodium hydroxide, 0.500 moles. sodium hydroxide, 0.0250 moles of sodium hydroxide. Stoichiometry is the same, 1 mole of sodium hydroxide, 1 mole of water, and so we've got 0.0250 moles of H2O. Again, finding a limiting reactant is just saying who makes the least amount. This guy makes the least amount, so HCl is our limiting reactant. So I'm going to go back and I'm going to show you how you should have kind of maybe known that just from the start. We have equal concentrations of both of these species, and the stoichiometry is 1 to 1 to 1 to 1. So because we have the same concentration but twice the volume, we have twice as much sodium hydroxide as we do from HCl. HCl is going to be our limiting reactant. We still would need to go through this calculation to figure out the number of moles of H2O that we make, but figuring out that he's a limiting reactant should be pretty straightforward. All right, just to give myself a little bit more room, I'm just going to go to the top of the next page here. And again, to contextualize this, we figured out in part A that our solution is going to be heated up a certain amount. So there's going to be a positive gain in heat for our solution. Our solution heated up. Our water heated up when we mix those two reagents together. The reason they heated up is that we had heat that was given off from our chemical reaction. We figured out, again in our first part, using the specific heat capacity of the solution times the mass of the solution and the change in temperature of the solution, that positive Q solution was equal to 693 joules. Again, this was our part A answer. What we want to do is we want to work now with Q reaction. So hopefully algebra for this makes sense. If minus Q reaction is positive 693, Q reaction equals minus 693 joules, right? This means that our reaction gave off heat. Negative Q means gave off heat. So our reaction gave off heat. And we knew that. We knew that this chemistry was exothermic. Okay, so the idea is this is the total amount of heat given off. We want to contextualize this. So we want to contextualize this, or what we'd call normalize this, to 1 mole of water. We want to have units of joules of heat per mole of water. So the idea is if we know that 693 joules was given off when we made 0.0125 moles, we can just divide those two to essentially scale it up and get it for 1 mole. So delta H of reaction, again in kilojoules per mole, is equal to Q of reaction divided by moles of water. Q for the reaction is minus 693 joules, and we just determined that the water that's formed is 0.0125 moles of water. And again, we'd like to have this, the problem asks us to calculate delta H in kilojoules per mole. So I'm going to take and multiply this by 1,000, or I should say divide it. 1,000 joules is 1 kilojoule, and I get an answer that's minus 55.4 kilojoules per mole water. So again, delta H of reaction being negative is okay because that means it's exothermic, and that's what we'd expect. So similar to the problems that we've seen before, we're talking about heat exchange between two different processes, but in this case, it's a chemical reaction that generates the heat, not a physical loss of heat by one substance.